Jai Hind all. Myself Dr. Amita Asthana from Ajay Kumar Garg Engineering College. In this video lecture, we will take the topic Opamp from the subject Fundamentals of Electronics Engineering BEC 101. This topic is particularly taken from Unit 3. Now this is a basic Opamp circuit in which we can see there are two inputs and one outputs. Right. So we have input number 1 and input number 2. This input 1 is mentioned as positive terminal or non-inverting terminal, and this negative is mentioned as inverting terminal. Right. If I give a waveform like this, and if it is get amplified by the Opamp, the output would be like amplified but in the same phase, right? And we can see if we give input at the non-inverting terminal, the output phase remains the same. Whereas if I give input to this particular terminal, in inverting terminal, then what we can do is the output will be amplified again, but the phase will be opposite like this. Okay, so this is the basic difference between the outputs of the two terminals, inverting and non-inverting. Operational amplifier is having a very high gain differential amplifier, and the gain is typically in few mega ohms, and it has very special unique property that the output impedance of the Opamps are very low, and this is the unique feature of the Opamps. Opamp not only the amplifies, but the CMRR, common mode rejection ratio, slew rates, and the offset voltage, offset current, these are definitely very zero, or you can say CMRR is very high and slew rate is very high, but there is no offset from the input which is going to be transferred at the output. So the Opamp is two inputs and one output, as we have already seen. If I talk of the equivalent circuit of the Opamp, it has been shown in the figure that we have two inverting inputs, and this are mentioned like this. The V1 is given at the inverting terminal, the V2 voltage is given at the non-inverting terminal. One thing we can note that V1 and V2 both inputs can be DC or can be AC also. So here the terminals are connected with some resistance or impedance that is called as input impedance, and this input impedance for the ideal Opamp, it is very high. Similarly, at the output we are taking at this particular node, and this is pin number 2, this is pin number 3 of the 741 IC, and this output is taken from the pin number 6 of the 741 integrated chip of the Opamp. Now this is the output impedance of the Opamp, which has been mentioned in the equivalent circuit, and the gain of the Opamp is mentioned at V2 minus V1, the differential voltage at the input terminals V2 minus V1, and the amplification factor is mentioned as A, and the total output becomes A and into differential voltage. These are the positive and negative supplies which are being given at the 741 IC Opamp at 7th and 4th terminal, the positive and input respectively. Opamps have very high gain that I already mentioned. They can work in two configuration, maybe open loop or maybe closed loop. Closed loop if the output is connected again to the inverting terminal, then we can call it as the op-amp is working in the closed loop situation. So in open loop configuration, when there is no feedback, the output back to the input in the open loop configuration, the gain can be exceeding 10,000 also. Whereas in the closed loop configuration, the gain is reduced, but in order to control the gain of the op-amp, the negative feedback must be applied, so that which though reduces the gain but improves many characteristics of the op-amp. As literally I told you, the op-amp is working in as a adder circuit, subtractor circuit, or you can say the integrator, it can work, the differentiator, all these working can be of the op-amp is defined for the closed loop configuration only, where we give feedback from output terminal to the inverting terminal of the op-amp. So here for the op-amp, we have one very important concept, that is we have virtual ground concept of the op-amp. Okay, what is this virtual ground concept? If I assume this particular op-amp to be ideal one, let's say I assume this op-amp is working in ideal mode, the voltage at this particular point V2 and the voltage at this particular time point V1. So from virtual ground concept and for the ideal op-amp, we say that V1 is equal to V2. In this particular figure, if V1 is 0 because it has been connected to the ground, the V2 becomes automatically equal to 0 as shown in the figure. So this is known as virtual ground concept for the op-amp. And one more thing is that the op-amp, whereas offering a very high gain, so we can note one more thing, that this output, here we are taking the output, so this output is again connected with the feedback resistance of RF, right? This output is connected as RF. Okay, this is the feedback resistor which is connecting the inverting terminal as well as the output terminal. So this feedback is very important, and this particular op-amp is working in the closed loop configuration, right? So here this is the input resistance, 1 voltage has been given as input at the inverting terminal, and that is how we can understand the op-amp configuration, or it is the op-amp circuit as we can say. Now I am going to cover some important basic concept for the op-amp numerical, and I will consider also some numerical aspects also. Let's say I am making one op-amp. This is negative terminal, this is positive terminal, and the output I am taking from here. Let's say I want to do a particular numerical practice for the op-amp. So I have, let's say, one resistance I am connecting. I am giving one, some V1 voltage at this particular point, and here I am giving some R1 resistance. Okay. Here also I am connecting one R2 resistance, and now I am grounding this particular point, right? Now what I am doing is I am connecting a feedback resistance between the inverting terminal and the output terminal. Now I want to give another voltage to my op-amp, and this voltage is V2, and I will give it through some R3 resistance. So this is this I have made a particular op-amp circuit, and this op-amp is working in the ideal mode. So what I am going to write is, let's say first point is op-amp is ideal, right? Op-amp is is ideal. One second, first I will assume that op-amp is ideal, and for next, if the op-amp is ideal, then there are so many things I have in my bucket. Like if op-amp is ideal, so I can apply a virtual ground concept rule. So let's say this particular point is A and this particular point is B. So from virtual ground concept, we have already seen that the potential of A point, let's say it is VA, and the potential of the B point, let's say it is VB. So from virtual ground concept, I can say that VA is equal to VB. That's all. So the goal is we need to find out the output voltage at the op-amp terminal. Okay. So this is my goal. I want to find this particular output voltage. This is my motive for the circuit. We want to calculate the VO at the output terminal of the op-amp. So how we will go? Now, if the op-amp is ideal, I told we have so many things for the consideration, and the other thing which I will consider, that there is no current going inside the op-amp. No current, because the input impedance is infinite. The input impedance of the op-amp is infinite because I am considering op-amp to be ideal one. So there is no current going inside the op-amp because it is offering open circuit, and there would be no current in the open circuit, no current flows in the open circuit. So there is no current inside the op-amp. This next thing is we have already, we can write it, no current is flowing inside the op-amp. Now to start the analysis, we should be aware, and we should check always one more thing, that is op-amp. I can see from this diagram, this particular output terminal is connected to the input terminal. So there is a feedback resistance. Right. So there is a feedback resistance. Okay. So I can see there is a feedback resistance also. So that means now I will start my analysis. The next step, the next concept which we are going to use for this particular circuit is Kirchhoff current law. So basically I will be using the Kirchhoff current law for the circuit. So first I will apply KCL at node A, right? We will apply KCL, Kirchhoff current law, at node A. Now if I go to the node A, I can see there is one V1 voltage. So I can assume one current I1 in this particular branch, and I can assume one I2 in this particular branch. So from Kirchhoff current law at node A, we know that sum of incoming current at node A should be equal to the sum of outgoing current. From there, I can say incoming current is I1. So I can write I1. Outgoing current is I2. So outgoing current is I2, and there is one more I current, but it is 0. So because there is no current which can flow inside the op-amp, because it is offering very high resistance. So I can say my question is now I1 is equal to I2. So if I1 is equal to I2, then I have applied my Kirchhoff current law at particular node A. So I have applied this one. Now what I know that whenever a current flows, it flows from higher potential to lower potential, right? And now what I can write is I1 is V1 minus VA, the voltage drop in the branch upon resistance R1 is equal to I2, the voltage VA minus 0, because next terminal is grounded. These two terminal I am taking considering. So from these two terminals, okay, the voltage difference is VA minus R2 minus 0. So this is VA, no? VA minus 0 upon R2. So I have applied simple Ohm's law. I have applied nothing else. Kirchhoff current law and Ohm's law. We all know that every time the Ohm's law, Kirchhoff voltage law and Kirchhoff current laws are always satisfied at any particular circuit. So we have done this particular equation. Now we can calculate this VA from here. I am calculating V1 upon R1. So we will find out VA is equal to this is by equation number 1. Okay, so we have already this VA we have calculated. Now I already know this VA is equal to VB. If this VA is equal to VB, that means now what my target is to reach this particular voltage VO. I want to reach to VO. So now I will apply again one more Kirchhoff current law at node B this time. So we will apply Kirchhoff current law at node B. If I will, let's say there I don't have any currents, no problem. We will, we will assume we can use some another, color. So this is, I3 and this is I4. So here also I can write I3 is equal to I4. If I apply Kirchhoff current law at node B, I can write I3 is equal to I4. Okay. Now again the same analysis we will do. I3 is voltage drop upon resistance and that would be V2. Since current is flowing in this direction, that means V2 is at high potential. So V2 minus VB. As we know, this voltage is VB. V2 minus VB upon R3. Try to understand and try to grant V2 minus VB upon R3. That's it I am doing. V2 minus VB upon R3. Okay. And then I will apply VB minus VO upon RF. VB minus VO upon RF. Now this I will solve. One more I have one more thing that I have VA is equal to VB. So at VB I will write V1 R2 upon R1 plus R2. Since VA is equal to VB, that's why I am writing this particular point. And now from this particular circuit, we can calculate this, no? Put this RF here, and from this particular circuit we can calculate equation. From this equation we can calculate the output voltage VO. So here the concept is very simple, that we need to check for the idleness of the Opamp. We will apply the virtual ground concept, and then we don't have any current which is going through the Opamp, and then we will apply VA is equal to VB, apply Kirchhoff current law, and after that you need to apply the you need to find out whether this feedback resistance is connected to the input or not. Check for the feedback resistance and then apply KCL, make equation, and you can get the desired result. So here always note Kirchhoff current law is always useful for solving the ideal Opamp numericals. Thank you.